When you write users, square bracket Alice, and instantly get back her record, something quietly miraculous happens. Even if that map holds 10 million people, the answer comes back in the same tiny sliver of time as if it held only 10. It doesn't search. It doesn't scan. It seems to just know where Alice lives in memory. That structure is the hashmap, one of the most useful inventions in all of computing, and underneath, it's wonderfully clever. To see the trick, start with what a plain array can and cannot do. An array is brilliant at exactly one thing. If you know the numeric position, slot number 5, it hands you that value instantly in constant time. But that only works for numbers. We almost never want to look things up by position. We want to look them up by a key, a name, a word, an ID. So how do we get an array's instant speed while using a key instead of an index? The answer is to build a bridge from keys to indices. We need some function that takes any key, a string like Alice, and turns it into a number we can use as an array position. Feed it a key and out comes an index. If we had that, we could store Alice's record at the index her key produces, and later find it again by running the very same function over the very same key. That function is called a hash function. A hash function has two essential jobs. First, it must be deterministic. The same key always produces the same number every single time, or we'd never find anything again. Second, it scrambles the key thoroughly, so that even very similar keys land far apart. The raw number it spits out is usually enormous, so we take it modulo the size of our table, which folds that huge value down into a valid slot. Key to big number to a bucket. Let's watch one fill up. We take each key, run it through the hash function, and drop its value into the bucket that the function points to. Apple hashes to one slot, banana to another, cherry to a third. Each one scatters off to a seemingly random but completely fixed home. There's no order here, no sorting going on, just keys flown across an array of buckets by the hash function. Now, the payoff arrives. To find a key, we don't look through anything at all. We hash the key a second time, which sends us straight back to the exact same bucket we stored it in, and there it is, waiting. One hash, one jump, done. That is why a hash map lookup is constant time on average. The size of the map is almost irrelevant because we compute the location directly. We never hunt for it. Say we ask for banana. The hash function runs, produces banana's number, takes it modulo the table size, and lands us on its bucket directly. We don't touch apple or cherry or any other entry along the way. We teleport to the right slot. Whether the table holds a dozen keys or 100 million, that junk costs exactly the same. This is the whole reason hash maps can feel like actual magic. But there's a catch hiding inside that modulo step. We're squeezing a gigantic space of possible keys down into a small number of buckets. Sooner or later, two different keys with two different hashes fold down to the same bucket. They collide. Now one slot needs to hold two separate entries, and if we're careless about it, the second one simply overwrites the first. We need a real plan for collisions. And collisions are not a rare accident, they are guaranteed. Here, grape and melon both happen to land in the same bucket. With more possible keys than buckets, this is mathematically inevitable, a fact known as the pigeonhole principle. If you have more pigeons than holes, then at least one hole must hold two of them. The question was never whether collisions happen. It's how gracefully we handle them when they do. There are two classic ways to cope with collisions. The first is to let each bucket hold more than one entry. The second is to let the extra entries spill outward into other empty buckets. Both approaches keep the constant time promise alive most of the time, as long as collisions stay reasonably rare. Let's look at each of them in turn, starting with the more common one. The first strategy is called chaining. Instead of a bucket holding a single value, each bucket holds a tiny list. When two keys collide, the new one simply joins the list hanging off that bucket. To look a key up, you jump to its bucket and then walk its short list, checking keys until you find the match. As long as those lists stay short, you are still effectively in constant time. Here's chaining in action. 3 keys have landed in the same bucket, forming a little chain of 3. A lookup for the last one hashes to the bucket, then steps through the chain 1, 2, 3, and finds it. The crucial thing is keeping these chains short. A bucket with 3 entries is perfectly fine. A bucket with 3,000 is a disaster, and we'll come back to exactly why that happens. The second strategy is open addressing. Here, every entry lives directly in the array itself, one per slot, with no side lists at all. When a keys bucket is already taken, you simply probe onward, try the next slot, and the next until you find an empty one. A lookup follows that same trail. It's more cache-friendly since everything sits in one contiguous array, but deletions get fiddly and a nearly full table degrades badly. So, how do the two compare on the things that actually matter? Chaining uses extra memory for its lists, but deletion is trivial, and it tolerates a crowded table fairly gracefully. Open addressing keeps everything packed into one array, which the CPU cache absolutely loves, but deleting an entry is awkward and performance falls off a cliff as the table fills up. Most standard libraries pick one of these and tune it very carefully. Now the honest truth about performance. On average, with a decent hash and short chains, every operation, insert, lookup, and delete is constant time. But the worst case is much uglier. If every single key were to collide into one bucket, your beautiful hash map degenerates into a plain linked list, and lookups become linear, walking all n entries one by one. The average is what you feel day to day. The worst case is what you guard against. So, what keeps you safely in that happy average case? Two things. First, a good hash function, one that spreads keys evenly across all the buckets, so no single bucket ever gets overloaded. A bad hash that clumps everything together recreates the worst case on purpose. And second, simply having enough buckets relative to the number of keys so that the chains never get a chance to grow long. Spread them out and keep them sparse. That second idea has a precise name, the load factor. It's just the number of stored items divided by the number of buckets. A load factor of 1/2 means the table is half full. As that number climbs toward 1, buckets start sharing, chains begin to lengthen, and the constant time promise slowly frays. Most implementations watch this single number nervously and flatly refuse to let it get too high. And when the load factor crosses a threshold, often around 3/4 full, the map does something dramatic. Sizes. It allocates a brand new, bigger array, usually with double the buckets, and then rehashes every existing key into the new table. Because the bucket index depends on the table size, nearly every entry may move. Watch the keys redistribute into the roomier array, the chains melting back down toward length 1. Resizing the whole table is obviously an O of n operation, since it touches every key. So how is insertion still considered constant time? Because resizes are rare. You double the size each time, so it happens less and less often as the table grows. And when you average that occasional big cost across all the cheap inserts in between, it works out to constant time per insert. That averaging trick has a name of its own, amortized analysis. You might reasonably wonder why not just use a hash map for absolutely everything. The trade is this: a hash map throws away order to buy raw speed. The keys are scattered by the hash, so you cannot ask for them in sorted order or efficiently find everything between two values. If you need ranges or ordering, a balanced tree with its logarithmic but ordered operations is the better tool. The hash map wins decisively at exactly one thing: instant point lookups. Let's place the hash map among its neighbors. An unsorted array inserts fast, but searching it means scanning the whole thing. A sorted array allows a logarithmic binary search, but inserting means shifting everything over to make room. A balanced tree gives you logarithmic everything and keeps the data in order. And the hash map, constant time lookup, and insert on average at the price of no ordering whatsoever, every row here is simply a different bargain. Once you recognize hash maps, you start to see them absolutely everywhere. They are the dictionaries and the sets in nearly every language you use. Databases lean on hash indexes for instant equality lookups. Hashes use them to find entries by key. Compilers track your variables inside them. Anytime a system can answer, "Do you have this?" or "What's associated with this?" almost instantly, a hash map is very likely doing the work underneath. A few traps to respect before you go. A weak hash function will quietly cluster your keys and murder performance without ever throwing an error to warn you. Using a mutable object as a key is dangerous. If the key changes after insertion, its hash changes too, and the entry is effectively lost inside the table. And never rely on the iteration order of the hash map. It's scattered by design, and it can shift the instant the table resizes. So, the practical takeaways. Expect constant time lookups, inserts, and deletes in the average case, and design your code around that. Keep the load factor low and let the table resize itself as it fills. Lean on a good, well-tested hash function rather than rolling your own from scratch. And the moment you need sorted order or range queries, reach for a tree instead, because order is the one thing a hash map will simply never give you. So the hash map's magic isn't really magic at all. It's one brilliant idea, turn the key itself into the address, wrapped in careful engineering to handle the collisions that idea makes inevitable. Compute where things live instead of searching for them, keep the bucket sparse, and you get lookups that simply don't care how much data you're holding. The price is order. And for an enormous range of problems, that is a price very much worth paying.